So in the last video, we covered Monte Carlo simulations, and in particular, we were focusing on how do we use Monte Carlo to model and estimate options price, right? How do we use it to price options? Now in this video, what we're going to do is we're going to find a way to answer the question that we left off with last time, which is how do we model volatility, right? So a little bit of a review. Monte Carlo is essentially a way for us to utilize the power of the law of large numbers, which says that as the size of our sample increases, the mean of our sample approaches the population mean. So Monte Carlo utilizes this fact to simulate M random stock prices and determine the option payoff from each of them, average the option payoffs, and then discount it back to today to determine the option price via no arbitrage. Now, the central equation that we realized from Monte Carlo is this equation, where this term, as you recall, represents the mean per period return, and this term represents the standard deviation. Now, epsilon I provides the random draw, right? So each time we're going to draw a random number that follows a normal distribution that has a mean of 0 and a variance of 1. And based on this, we will determine the size of this term. From there, we know what to add here, and then simulating across each time period, we will get the ending stock price. Using the ending stock price, we can raise both sides to the e power, and we can get st, right? So from there, we can determine the call price for that particular path, and doing m different paths and discounting to today, we will get the fair price for the call option. Now, one of the questions that we left off with last time was, what is this sigma and what is this r, right? So as you recall, r represents the risk-free rate and sigma represents the annualized standard deviation. One of the powers of the Monte Carlo approach compared to something like the Black-Scholes, which has a closed form solution and assumes constant risk-free rate and constant variance, is that we are able to vary this for each time period. And this raises the question, therefore, of how do we model sigma? How do we model the variance, right? And this is what we're going to cover in today's video. So I put together this PDF, and today we're going to be starting from chapter 6, which is one of the simplest ways to model volatility, right? And it just says that volatility follows a AR1 process, which means that it is mean reverting. Now, if you think about this, it does make sense that volatility would be mean reverting. So if you think about how much a stock moves on average, usually it's hovering around a certain level. And then during a major earnings report, it'll deviate from that level significantly, but then it'll go back to where it used to be. So AR1 process seeks to capture this. Now, when you're first looking at this formula, it might seem intimidating, right? But once you take it apart into 3 separate pieces and understand what each piece means intuitively, it becomes much more easier to memorize. So let's look at piece 1. So piece 1 is saying that if we have some, random variable that is x, then piece 1 is saying that if, one time period is passed, then we're going to get delta, which is the period of the length of that period, times rho, which is the strength of the pole, times the mean, which means we're going to get this much closer to the average of this value, right? So this is the mean reverting term. And then we're going to look at piece 2. what piece 2 is saying is that xt is our current level today, and xt plus delta is our level 1 period from now. And it's saying that, because delta is a very small number, we're going to stay mostly at today's level. So it's saying that pretty much tomorrow's level is going to be just a slight deviation from today's level, but it's going to depend on rho, which is the strength of the pull. And then piece 3, this is where the random component is. So remember in last lecture, we talked about the fact that because the delta is the variance typically scales with delta, the standard deviation typically scales with the square root of delta. So if you look at the term in the front, excluding this omega term, this term represents the standard deviation, where this specific term represents the size of the shock, right? The larger this is, the more random our model becomes. And then the square root of delta scales linearly with time, and then this omega term is a random shock. And we're going to simulate this as a random draw each time that has a mean of 0 and a variance of 1. Okay, so this is our model right here, and this applies to any random variable, right? So it's just a recursive relation relating the level that this random variable is at today, which is xt, with the level that it'll be at tomorrow, incorporating the fact that, first of all, it'll stay relatively close to today's value. It'll try to get closer and closer to the mean, and there is this random component to it. Okay, so this turns out to be a relatively good way to model volatility. And it turns out that when we try to answer the question of what x of t is, there could be 3 possible answers, right? Remember that we're trying to model the volatility term here in the Monte Carlo simulation, sigma. Now, the 3 ways that we can model this is, first of all, we can say, okay, so we can just let the random variable be sigma. The second way is that we can let the variance, sigma squared, be this x term. Okay, and then the third way is we can let the log sigma be this x variable. So all we're doing in each of these 3 methods is simply replacing this x term with either sigma, sigma squared, or log of sigma. So you might be wondering, okay, why do we use log of sigma? So I'll give you a second to think about this. And this actually turns out to be a very brilliant way that we can enforce a sigma that is always positive, right? How do we do that? Well, think about it. No matter if this term on the right is positive or negative, right? Even if it goes below 0, let's think about raising the power of both sides, raising e to the power of both sides, right? Raising e to the power of log sigma, that just gives us sigma on the left. Raising e to the power of whatever's on the right, regardless if it's positive or negative, is going to give us a positive number, right? If the right side is positive, we're going to get a large positive number, and if the right side is negative, raising e to the power of it just gives us a small positive number. Now, what this allows us to enforce is the fact that sigma is always positive, right? You can never have a negative standard deviation, which is a problem with method 1 and method 2. Okay, so these are the 3 ways that we model variance. And I created these graphs. I plugged in a few parameters for these each of these components, and I created 3 graphs of what each variable looks like, right? So here we have the time step on the x-axis, and we have the sigma term on the y-axis. And this is just saying that, sigma follows the AR1 process, sigma squared follows the AR1 process, and log of sigma follows a AR1 process. And as you can see, they all have distinct characteristics. However, what we notice is that, especially for the case of log sigma, the sigma itself never goes below 0, right? As compared to some of these other ones where it tries to go 0, and we would have to find a way to effectively cut it off. Okay, so right, and then so those are the ways that we can use an AR1 process to model volatility. And these are some of the ways. So as you can see, right, comparing the log return equation with the volatility equation side by side, we can see that the commonality they have is they both have this standard deviation term multiplied with a random draw component. So here with the log returns, the random draw is symbolized by epsilon, and here with the volatility, the random draw is symbolized by omega. But regardless, at each point in the Monte Carlo simulation, so imagine you're on a path and you're zooming in on one specific time period. Now what you're going to do is you're going to first use this model, right? The AR1 process to determine the standard deviation. Here you're determining the variance, and then taking the square root of that, you're determining the standard deviation. Now, once you have the standard deviation, you have sigma, right? Sigma is the standard deviation. And then, you find some other way to determine the live risk-free rate. Now you have everything in here except epsilon. Now, what do you do with epsilon, right? Epsilon becomes a random draw, just like how we performed a random draw for omega. Now, one of the fascinating things about this approach is that people sort of figured out that epsilon, which is the random draw for volatility, actually tends to be correlated with the omega term. And it turns out that each of these tend to be IID, right? They're independent and identically distributed over time, which means that the omega term, because it's a random draw, omega t is going to be independent but identically distributed from omega t plus delta. However, and the same applies to epsilon. However, at each moment in time, these two variables tend to be correlated. And we symbolize that correlation with this rho, right? This rho represents the correlation between the two random draws. And a fancy word that we term this is IID through time, but contemporaneously correlated. So that's all that's saying is that, there's a correlation between the random draw term for the volatility and the random draw term for the volatility of the volatility. Okay, so that's all the AR1 process is. It's a way for us to model the time-dependent volatility using a mean reverting process. And this fits nicely within our original Monte Carlo framework. So all that is a way for us to determine sigma here to use in our Monte Carlo simulations. All right, so if you enjoyed this video, please give me a thumbs up and subscribe. And if you're into quantitative finance, or if you're into options pricing or physics, please subscribe and stay tuned. Thank you. Bye-bye.